Hello, and welcome to Hands-on Arduino, Part 7A. The fact that I have an A there should communicate to you that I'm going to have a little series here of videos. So this is just the first one. I'm not even sure right now how many videos it's going to come out to be. Control Inputs Part 1. So that also tells you something. This subject is about autonomous robots. Autonomous robots are useful for many applications. They require knowledge about lots of different things. And so as a result, they cover most of the kinds of things that an Arduino can do. And they're just fun. It's kind of a high-tech toy. So that's what we're looking at. Our autonomous robot is going to be built around this kind of a structure. And this is kind of like a high-level block diagram, although these aren't exactly blocks. They're more like kind of triangloids. But anyway, 3 parts. We have locomotion. That's the part that drives the wheels. We have sensing and communication. That's the part that would, for example, this would use Wi-Fi to communicate with a base station, for example. This would involve the use of sensors for situational awareness, to see what's going on around, to see if there's obstacles, to see what's going on. And then we have the supervisor that oversees all of this and that tells the system what to do, each of the different parts. And so all 3 of these components of this require some intelligence. They all need to communicate back and forth to one another. And so I'm going to focus in this lecture, actually these next few lectures, on locomotion. So in locomotion then, we want to see how to drive our system to do something, just basically drive the thing. Okay, so there's obviously a lot that goes into this, and we'll talk about that. So in terms of locomotion, these are the main topics I'm going to be looking at. We have motor driver basics, that is, how do you actually drive some motors? So we're going to look first of all at joystick control. So control inputs 1, guess what our first control input is? It's going to be a joystick. And we're going to see how to use a joystick to map what inputs the joystick gives into meaningful motor information. We're going to have a session on motor driver control, how to actually drive a motor driver. Sounds kind of weird. And then we're also going to look at, instead of using the joystick as the input to our system, using an RC control for our system. So what this allows us to do is it allows us to go untethered. So using a joystick means that we have to have a tether to our autonomous robot. So this is just under locomotion. This is just these 2 inputs are used to give the system something to do, somewhere to go. Okay, so the system by itself, without the supervisor, without the other things, the sensors and so forth, it's not going to be autonomous at all. So here, we just have the basics of getting the thing to move. Okay, what's involved in that? And so for some of you, this is pretty intense stuff, and I hope it doesn't overwhelm you, but we'll try to keep it as simple as we can. Okay, so driving large motors. In general, the thing about driving large motors is that they generally require large currents, in particular, much larger than the 40 milliamps an Arduino can put out. Also, we generally want what's called back EMF protection. So that is, if you switch a motor has electrical windings in it. That winding, when you apply current to it, builds up what's called a magnetic field. When you take the current away, that magnetic field is still there, and it collapses, but in the process of collapsing, it can produce very large voltage spikes, very large voltages, and so that's the protection that we're talking about here. We also want our motor to be bidirectional. That is, we want it to go forwards and backwards. And we generally want some kind of logic required to tell it to go. Now, for large motors, one of the most common circuit components is what's called an H-bridge. And we talked a little bit about an H-bridge in the lecture number 5 about various interfacing of circuits. So we're going to talk in more detail now about the H-bridge. So 4 switches in an H, okay, and the motor is in the middle. The motor is not grounded. Both of these sides are floating and are controlled by the switches. So the nice thing about the H-bridge is that it only requires one voltage supply to go positive direction and negative direction. So depending on how you switch these switches, you can go positive direction or negative direction. Here are 4 useful configurations for the H-bridge. Okay, so free running means basically coasting. Okay, so when all the switches are open, it's coasting. When the 2 bottom switches are closed, then you have a loop here, and the resistance in the windings of the motor will cause this thing to slow down faster than if you just let it go free. Okay, it'll slow down faster. So the friction in the system will generally cause the motors to eventually slow down and stop, but with resistive braking, it will stop a lot quicker. Okay, so that's the second option. Then we have the motor turning right and the motor turning left. And so notice we have diagonal switches that determine whether it's right or left. Notice that what we never have in any of these 4 configurations, what we never have is this. We never have common switches that are closed at the same time. Okay, this is not allowed, and the reason it's not allowed is because basically that's shorting out your power supply. Okay, and so this is a good way to fry your battery. In fact, I just did that recently, and it didn't fry the battery, but it unsoldered one of the connectors inside the battery, and so it was pretty much not usable. So these are the main configurations. These 4 configurations. Here, this is resistive braking low. We could also have resistive braking high, where these 2 switches are closed and these are open. Okay, so notice that the way this goes, the current can flow this way, and if we switch them in this configuration, it goes this way. And so if you think about what's going on with this situation, if we want full speed, then we would just leave it in this configuration. Okay, full speed turning to the right or clockwise, counterclockwise. Full speed is that's the full amount of energy that can be supplied to the motor by the battery. Is if you just leave them closed, completely closed, and then this motor speeds up, and then it reaches a final speed. Okay, a maximum speed, and so that's basically what's going to happen in this case. But you don't have to go full speed. You could go at a reduced speed with this same thing by opening and closing these switches. So by opening and closing these switches, we can have the motor turn in various ways and at various speeds. So depending on how long this thing is energized, then that will determine the speed. So if it's energized 100% of the time, then it will be full speed. If it's only energized 50% of the time, then it will be half speed. And so that's the concept of pulse width modulation. So here's an example of a video that involves pulse width modulation. Here is the voltage signal that I'm applying to the motor. Okay, and so let's here we can see the switches. So notice that switches are going through this direction. They're opening and closing. And notice that they're opening and closing. They're open as long as they are closed. So this is what's called a 50% duty cycle. And notice the 50% duty cycle is the same, basically gives us the same speed. So the speed here is the slope of this curve. So this is the position of the motor with respect to time. And so notice that I have three different frequencies for pulse width modulation. I have a low frequency, medium frequency, and a higher frequency. And so notice that the speed basically is the same. So except at the very beginning when the motor kind of winds up, the speed is basically constant. That is, the slope here is basically constant as we do this pulsing. And so you can think of it as being like if you're in your car, especially if you have a manual transmission. Okay, in a manual transmission, you engage the gear, you hit the gas, and then you let off the gas. You hit the gas, you let off the gas. If you just keep pumping the gas, the car will basically go at constant speed. It'll speed up and slow down, but it'll be roughly constant. The speed will be roughly constant. And so this is actually the speed here is actually the slope of this line. And so you could see, let's run this again, how okay, here we go. So you can see the motor's turning as we pulse the energy through the motor. And so notice that the speed at which we pulse it does not affect it nearly as much as the duty cycle. That is, how long is it closed compared to how long it is open. Okay? So the duty cycle is actually the time that it's closed, the switches are closed, with respect to the period. Okay, in this case, we have 50% duty cycle, even though we have different frequencies that we're working with. So the frequency is not the critical thing, it's the duty cycle that's the critical thing in determining the speed of the motor. It's 100% duty cycle, that is, if it's on more than it's off, then you will have a different situation happening. Okay, so now if you noticed, we basically had all the switches open, and then we would close these alternately to make it go, and it would go in one direction. What happens if we alternate switching these with these? Well, this is what happens. So we're alternating switches, and so you can see the motor is kind of rocking a little bit, but it's basically staying in the same place. And this is a graph of the position. The position drifts a little bit, but it basically stays in the same place. And again, the frequency of the pulse width modulation doesn't change. So notice again, this is 50% duty cycle. 50% duty cycle. And regardless of the frequency of that duty cycle, it still does basically the same thing. So what's happening here, by alternating these sets of switches, we're applying positive voltage to the motor for half the time, and then negative voltage to the motor for the other half of the time. And it's like the two cancel each other out. And so we actually get zero or very small movements, even though the voltages are not small. The voltages that are applied are not small, and yet we still get we still get small movements. Okay, so that's something about the duty cycle. The next thing I want to show you about the H-bridge is I want to actually change the duty cycle. So I want to go from 0% duty cycle to 100% duty cycle, back to 0% duty cycle, then to 100% duty cycle, so forth. And so basically what this pulse width modulation signal is, it's actually sinusoidal. It's a sinusoidal pulse width modulation signal. Again, it's just positive. So let's see what happens when we do that. So notice that when we stop, when we go to 0% duty cycle, the thing stops. The voltage causes it to stop. So here we've left it open, and it stops, and now we have 100% duty cycle, and it speeds up, and so forth. So we have the highest speeds, that's the steepest slope, corresponds when we have the highest duty cycle. And the lowest speeds, that is when it has like zero slope, is when we have zero duty cycle. And so you can see I can adjust the speed of the motor by adjusting the duty cycle of the pulse width modulation. So it's helpful to understand what's actually happening in all of this. So here I've just shown a pictorial diagram of switches. Basically this is the way all of this works. So in general, when we come to a motor driver, we have certain requirements associated with it. Generally, we want bidirectional motion. We want independent power supply. That is, it would be good if you had a power supply just for the motor driver, not for the Arduino, for example. So that the Arduino is not on the same power supply as the motors. So as the motors start to wear down their batteries, that doesn't wear down the Arduino. We generally need sufficient current to handle the task. Okay. We either want a pulse width modulation input signal or an on-off signal. So in other words, we want it full on, full off. So those are the kinds of things we would like. An enable or disable capability. That is, if we want to disconnect the motors and shut them down, that would be nice to have. It would actually be nice also to have braking capability. And finally, it would be helpful to have current sensing capability. So the torque that's generated in the motor by the windings and all that stuff is a constant times the current in the windings of the motor. And so, in particular, when you have a DC motor that stalls, that is, let's say your thing goes along and it gets stuck, and so the wheels are not turning. Okay, if the wheels are not turning, that condition basically requires a lot more current than when it's just running smoothly. Okay, it requires a lot more current, and so that's called a lock rotor torque. And so it would be nice if we could sense the current to see if we're in that locked condition. That would tell our system that, for example, our system is stuck. The robot is stuck, and so we would want to be able to tell it then how to get out of that stuck condition, especially if we're in an autonomous mode where it's basically running by itself. Okay, for locomotion, the platform we're going to use for this is a Wild Thumper vehicle. So you can find these in a number of places. They're really pretty cool. They have independent suspensions. So each of these wheels has a motor that's attached to it. So there are 6 motors, 6-wheel drive. So it's pretty sweet. 6 pulse width permanent magnet DC motors. Basically, they connect them so that 3 motors are in each side. So you're actually only controlling 2 sides. So it's like controlling 2 motors, even though you're actually controlling 6 by putting them in parallel. Each of these motors has these conditions: operating voltage between 0 and 7.5 volts, starting voltage 2 volts. That means, so these are the voltages you want to use your system within. You don't want voltages larger than plus or minus 7.5 volts. Starting voltage 2 volts means don't expect the system to move if you apply voltage less than 2 volts. The rated voltage is 6 volts. The rated voltage is the recommended maximum voltage. That's not the absolute maximum voltage. That's the absolute maximum voltage. This is the voltage that they recommend that you use if you're going to run it 100%. If you're going to just leave it full on all the time, this is the voltage they want you to use. No load current. So that is when you're not doing anything, this is the current that's like the minimum current that's going to be applied. The average running current obviously it depends on what voltage you apply. If you apply 7.5 volts, you're going to get 1.7 amps, about 1.7 amps for this thing to run at. But the locked rotor current is 5.5 amps. Okay, so that's for each of the motors. So if you have 6 of these motors altogether, or rather, if you have three of these, three on a side, each side then is going to require 16.5 amps. Okay, it's going to require that. And if your circuit is not able to supply this, two things are going to happen. One, you're either going to fry your circuit, or you're going to send your circuit into la-la land. Okay, some circuits they have self-protection. That is, if you try to draw too much current through it, it kind of shuts itself down. Okay, so neither of those are particularly good options if you're autonomous, because you don't want to have to run out there and reset the thing and blah, blah, blah. You don't want to do that. Okay, so your motor driver basically has to be able to handle 16.5 amps. So in terms of locomotion, this is kind of a block diagram for how we would put together a power driver for the robot. So we have the motor driver, and this is going to be a circuit that's specifically designed to drive motors with a power supply. Okay, we're also going to have our Arduino that's going to connect up to this. And so it's going to have its own power supply. So these are the independent power supplies. This is a low power supply. This is a high power supply. So we have that. Now, it's very common to want to actually have a relay in between the power supply and the motor driver, so that the Arduino can shut the power down to the motor driver in the event that it sees something, or it feels like it needs to do something to prevent the motors from doing stuff. So this is another option. So this is a not uncommon option for a motor driver situation. So instead of having the power supply connected directly to the motor, the motor driver, it goes through a relay. So the motor driver is going to contain your H-bridge and so forth, and other circuitry that's needed, like I said, to protect itself, so forth. So you can get online and find all kinds of parts. So here is a 5,000 milliamp hour battery. 5,000. So that's a pretty good deal. So this battery is 7.4 volts. So that's like the absolute maximum. But if you do pulse width modulation, you can actually get away with using 7. Even though 7.5 is the maximum voltage, 7.4 is not too bad to use in a pulse width modulation setting, as long as you're not running it all the time at full speed. Here is a way of connecting up an Arduino to a power supply. So in this case, it's a 9-volt supply. You can just use a barrel jack connector to a 9-volt supply. Relay shields. There are shields that do relays. Okay, and then there are motor driver shields. So this is an example of a motor driver shield. This is actually the one we're going to be looking at. So in terms of the block diagram layout, this is the kind of layout that we would be using. So initially, I'm going to start off as my control input. I'm going to use, again, eventually I want it to be autonomous, right? But for now, the control input is just going to be a joystick. So this one of these little joystick dealies. Okay, so you have two directions, and it provides two analog voltages that can be used. Okay, and so we have a relay shield also that we can use. We have this motor driver. This motor driver actually can drive two sets of motors. Okay, each of these, this particular motor driver is able to handle 25 amps. So that's definitely more than 16.5 amps. And so each of these can handle 25 amps. And so this one circuit is able to handle all of the motors. And so that's cool. One little circuit. And so notice that in connecting these, I have certain pins that I need to use between the Arduino and the thing. And so now the joystick. What do we do with that joystick? How do we work with it? So here is our little joystick thingy, and so you can see that I can basically give an analog voltage in this axis, an analog voltage in this axis. Okay, and so I have two axes of analog input that I can provide with this one device, and so I can roll around in a circle or do other things. So it's a handy little doodad. And so our our main task in this hands-on Arduino is actually, how do I use this joystick to provide a meaningful input to our Arduino so that we can control the motors in a way that makes sense. Okay, so if you think in terms of the motors, you're basically going to want to use a pulse width modulation to determine speed. Okay, so you need to communicate not only the speed, so I can adjust the speed. If I go all the way over, that's full speed, but if I do partially, I should get partial speed. And if I roll this around, I should be able to get different speeds going in different directions. So partial speed in this direction, partial speed in that direction, and so forth. Okay, so I map the kinds of things that I need in order to try to figure out how to get the relationship that I need in order to drive something like an Arduino. So if I go through and I look at my joystick and I see what kind of signals do I get. So I have this thing set up this way so that this axis is the y-axis, this axis is the x-axis, and so I have it now set up this way. So if I, depending on how I move it, I can get these various positions. And so if I go through and I actually take readings of the voltage in the various places, the analog input is going to, remember, it's going to give me a voltage between 0 and 1023. And so these are the voltages that I get. Notice I get two voltages because I have an x and a y axis. So notice I have 0, that's when I'm all the way down here. And 511 is basically halfway between 1023 and 0. And so these are the voltages that I get. And then when I'm at the very center, I have 0, 0. I'm sorry, not 0, 0. 511, 511. Okay, so when I'm at the origin, I'm actually not getting 0, 0. I'm getting 511, 511. Okay, two numbers. So notice, so we have these ordered pairs of values. So that's what's happening. That's what this thing is giving to us. Now, what is it that our motor needs for it to make sense? Now, if you recall, the motor is set up with 3 motors on each side, right? 3 motors on each side. And when you rotate the motors, all the motors rotate together in the same direction. Okay? And so depending on what you want the thing to be doing, so in other words, how do you want it to respond to this? That's an important thing. It's not trivial to think about that. Okay? So in particular, this is the kind of thing that I would want. So if I push it up, I want my motor to go ahead straight, full speed. If I push it all the way up, I want it to go ahead straight, full speed. If I push it down, I want it to go reverse, full speed. If I push it to the side, I want it to turn 90. I want it to be turning, right? And if I push it this way, I want it to be turning. And so depending on the inputs that I get, I want to do different things. So if it's full up, again, I want it to go full straight ahead. So what does that mean in terms of the motors? So positive voltage means the motor is going to turn clockwise. Okay? So positive voltage. So clockwise, if you want, so notice the way I have my hands. The way I have my hands are exactly the way the motors are going to turn. So if I want all the motors to turn this way, what does that mean in terms of the direction they're turning? Well, so notice how my wrist is doing the turning. Okay, so if I now put them this way, notice that basically means that my motors need to do that. That is, one needs to go this way, the other needs to go the other way, right? And they need to go full speed in that way. And so that's why I have here clockwise, full speed, 255. Remember, for pulse width modulation, 255 is the maximum value. And then counterclockwise, 255. So clockwise, 255, counterclockwise, 255. That's what I want to have happen when this guy receives that voltage. Okay, so that's full steam ahead. Full steam reverse is this way. It's just the opposite. Counterclockwise 255, clockwise 255. Okay, so, and similarly, what this is going to do is this is going to turn them, when I push it off over to the side, I want it to rotate in opposite directions. And instead of going the same direction or the reverse, positive or negative, I want it to go opposite directions so that the vehicle will turn. Okay, and so notice that these are both counterclockwise 255. These are both clockwise 255. Okay, so this is the mapping that I want between the inputs that I receive and the kinds of outputs I want to be feeding to my motor driver. And also here, this value is 511, 511. I want this value to be 0, 0. That is, when I'm in the middle here, that is at rest like this, I want my mobile robot to be stopped. Okay, 0. Okay, so now how do this is the mapping between the joystick input and the output that we are expecting from our motors. Okay, so this is a mapping, and it involves both the X and the Y inputs, and it gives U and V as outputs, or M1, M2 outputs. Okay, so here I've gone ahead and taken all of these pair. So I have this pair that connects with that pair, this pair connects with that pair connects with this pair connects with that, and then the 0, the center corresponds to that. And so I have 5 pairs altogether. So here they are. And notice that I've rounded them to a power of 2. Okay, so this is 512, 1024, 256 instead of 255, and so forth. And that just makes the rounding easier. So we can take this now, and we can show that the relationship between the J's and the M's is given by this relationship. Okay, so I have JX, JY, that's joystick X, joystick Y, M1, M2. So this is the relationship. It's like, now, how do I... It actually took me a little while. Actually, to obtain this relationship, I actually had to use some linear algebra and so forth to actually get it. But let me just show you that it actually is working. Okay, so for example, let's suppose we want to be in at 0, at rest. So that's this place. So instead of 511, 511, I have 512, 512. So what happens when we put 512 and 512? We get 0, right? What happens if we put 512 and 512 here? We get 1024 divided by 2 is 512, which is 0. Okay, so we get 0, 0. That's exactly what we're expecting when we're at the neutral point. And so forth. You can go through and show that each of these pairs will give these pairs when using these formula for JX and JY. So what the value of this is this tells us what to do for every value of input, JX and JY. And what we have used to create this relationship are the extreme points. Okay, all the way one side, all the way to the other, all the way up, all the way down, and in the center. Those are the extreme points of the motion. And so we have used that. We've developed this relationship. And so now we have that. But there's one more thing that we generally want to consider, and that is we will often want so the only time your motors will actually stop is when you're dead center here. Now it turns out these little guys don't ever actually go to dead center by themselves. Okay, they're always slightly misaligned, and as a result, you will get something non-zero. In other words, your mobile robot will just sit there and do something zany, or whatever. It'll be wasting power is what it'll be doing. Okay, and so what we want to do then is we want to create what's called a dead zone. That is some region near the origin, so that when I'm in that region, I am going to just set it to be 0. Just set the value to be 0, so that I have a larger range of values for which my function is 0. And so once I go out of this, then I start having voltages that are non-zero, and I'll start heading in that direction. But this will basically prevent me from trying to apply voltage to my motor and have it waste power. So we saw, for example, that the motors themselves require 2 volts just to get moving, right? And so if you set these to be 2 volts, that's pretty good, right? So here's our Arduino code. So I set up a time and a past time. X and Y are the inputs from the joystick. Notice they're floats. M1 and M2 are the values, the pulse width modulation values for the 2 motors. And so I start this up so that I use serial begin so that I can display results on the console. And I set my pass time using the list. So very simple setup program. Here's my loop program. I first compute the, I first check the time, and then I see if the time minus the pass time is greater than 500. That is, if a half a second is passed, then I'm going to do all this stuff. Otherwise, I'm going to just going to sit there and do nothing. Right? I'm going to bypass all this. So this is just a simple loop to do stuff only when the time is about a half a second. So every half a second, roughly, not precisely, but pretty close, I'm going to do all this stuff. So what is it going to do? It's going to read the analog X and Y. Notice that I'm going to use these formulas that I developed. Okay, and I'm going to constrain the values so that whatever values I get, I'm going to make sure I'm not greater than or less than minus 255, not greater than 255. So that's what constrain does. It prevents you from accidentally getting values that are too large, which actually happens. It's part of it. It's because of the way this thing is made. Anyway, it can happen that this formula will give you a value that's larger than 255. You mean even like 260, something that wouldn't make any sense, but it happens. So this constrain basically constrains that the pulse width modulation value is going to be between plus or minus 255. So plus 255 corresponds to clockwise 255. Minus 255 corresponds to counterclockwise 255. Okay, so I'm computing these 2 pulse width modulation values for the 2 motors. And this is where I constrain them. So I'm going to take the max, if the maximum value is less than 20. So if I'm within 20 values, pulse width modulation values of the origin, I'm going to just set the value to be 0. Okay, so as long as I'm within this region, and where did I get this value 20? Actually, I got it by experiment. By trial and error, I found that works pretty well. Okay, so yeah, sometimes you do this by experiment. And so then I'm printing out the X and Y values that are taken in. I'm printing out the M1 and M2 values that are taken in, and so that's what you'll see on the console. Okay, so here's our Arduino code, and we can see. So there's the whole program there. It's not very long, and then we're going to go ahead and upload that. So it's uploading. Okay, so it's running now. Here's our serial monitor, and so you can see right now. Notice that it's not at 512, or 511, which is where it should be. So you can see it's off a little bit, but we're still outputting. So these 2 values are the X and Y values. These 2 values are the pulse width modulation values we output to the motors. Okay, so even though this is not 0, we're still putting out a 0. Okay, and so as I push this all the way up, boom. So we're basically getting 255 and minus 255 when we're all the way up. When we're all the way down, minus 255 and 255. Okay, so you can see it's actually working over here. Both of them are the same sign. Notice that it's not exactly the same value, and that's partially because it's actually difficult to get them exactly lined up. And then the other way, they're both again the same sign. So when you're going positive and forward, the 2, when you're going forward and reverse, the 2 have opposite signs. When you're turning right or turning left, they go opposite signs. Same sign. And so I can get intermediate values here, And what that would correspond to then is that would correspond to turning at some speed with, so when one wheel is turning slightly slower, so if this one is slightly slower than this one, then what's going to happen is, because this one's going faster, it's going to push the thing around. And what ends up happening is that since you have 6 wheels all trying to push, the wheels on the slow side are going to be slipping. Okay, they're going to be slipping as these guys go around. So it's kind of like when you have a marching band, the guys that are on the outside have to march faster than the guys on the inside. It's that same kind of thing. And so this actually gives us what's called proportional steering. That is, it allows us to go to not just have to turn 90 degrees or not. So when you're off to the side, what basically is going to happen is the robot is going to rotate in place. Okay, it's going to rotate in place. And so what this allows you to do is to rotate in place or to turn. So what basically that means is you're stopping going and you're actually just rotating, right? So what this allows you to do is actually continue going and turning at the same time. So that's what the proportional steering allows you to do. And so because you have 2 different motors going at different speeds, you can have that kind of thing happening. And so this is the autonomous robot input 1. Stay tuned for input 2, where we're going to look at using an RC controller instead of the simple potentiometer. So again, the problem with the potentiometer is that we have this tether that we have to worry about with our robot.